Hello, everyone. Welcome to this J Champions Conference talk. Today, we have Tom Cools, who's a developer relation engineer for Timefold, obviously also a Java champion, and the leader of the Belgium Java user group. So, how are you, Tom?
I'm doing quite well. So it's probably important to state first that I'm not at home. I don't have such a fancy venue at home. I'm at the Dublin Java user group tonight. So woohoo! I don't know if the mic picked that up, but there's quite an enthusiastic bunch here. So I'll be doing this talk hybridly, so both remote and here. And they actually just gave me a gift that I sort of have to show you now. So whenever you talk at the Dublin Java user group, you get one of these specialized custom artworks, and they gave me this one.
Nice.
It's a bit blurry, but they have Duke, it's me on a sled, and the Timefold logo. So that's what the talk is going to be about anyway. So thank you so much for this beautiful artwork. All right. So I'm excited to share a few things today. So ready to get going.
Cool. So let's go for the slides, and I'll let you go, and you can ask the questions in the comments. I'll pop in. That's for the crowd. I'll pop in if there's anything going on interesting that I need to tell you. Let's see you later.
Okay. Perfectly fine. See you later. All right. So good evening, everyone. It's a bit of a weird topic to state in January, but we're going to talk about Santa. I know that the holidays are behind us. I hope everyone had good holidays and that 2026 has started quite well this year. But Santa already is planning for the next year. It's only 331 more days. Oh.
We lost you. You're mute. You're muted now. Can I?
Yeah, it seemed like the mic was... When did I go to mute, Henry?
After saying Santa something. So like 10 seconds ago. It's fine. But
okay. I'll check if the mic keeps giving out. I'm switching to the other mic anyway. Okay. So let's start again. Santa, holidays behind us. I have a counter here. It's a real counter. But Santa has a lot of things to plan. One thing, toys need to be created. Now, I use Gen AI to make Santa look as corporate and depressing as possible. But these are the elves creating the different toys. Workers need to be assigned shifts. So you have different elves. They each need to be assigned shifts. They probably get some time off as well. Maybe they need to work some overtime closer to Christmas, but that needs to be scheduled. And finally, Santa needs to figure out the best route to visit all the children on the good list, not the naughty list. They are out of luck. Now, this is surprisingly tricky to do. These are all what we call planning problems. Now, planning problems are basically you have goals that you want to achieve. I want less travel time. I want to assign the best shift for the best people. You have limited resources. Santa is a bit special. Santa has this magic that will make my demos much easier because things that I can't really explain, I can say Santa magic. But typically, you have limited resources, you have limited employees, limited vehicles that you have to drive around. And you need to do it under constraints. You can't just be in two places at the same time, for example. That's one of the constraints. So our focus for today, what I want to show you is together, we're going to solve the routing problem, visiting all the nice children on the nice list. So what are we going to do? We're going to minimize Santa's travel time because he is getting a day older, just like all of us. So if we can reduce his travel time, more time for him to sit on the North Pole and eat some nice snacks and some drinks or whatever Santa actually likes. We have one resource, magical sleigh, and we have some constraints. There are some Santa things that will become clearer later in the presentation. So let's tackle that problem with our favorite programming language, which is, of course, Java. Thank you for your enthusiasm. So how would you solve this problem in Java? What classes would you use, for example? How would you model this domain? Let me be a bit more specific. What would you need? Which classes? Date will be one of them, yeah. Maps, yeah. What, much more simplistically, we need a vehicle. And we probably need something like visits. And then each vehicle will have a list of visits, right? Because that's the visits that vehicle will have to visit, obviously. And the list is ordered, so it means there's a specific order in which you will visit these locations. So that's the simple class diagram. Now, how are we actually going to fill that list of visits? Because depending on what order we fill these visits in that list, it will be a good route or it will be a horrifically bad route. How would you do that? Yeah. So first create a graph, then create a structure. That's already a bit more advanced approach that you could take. One of the simplest approaches is what we call a greedy algorithm. And a greedy algorithm, the definition of that is make locally optimal choices at each step, but don't consider effects later in the structure. So I don't like definitions. I like silly demos. So a greedy solution is, let's say that I add a few visits. So the visits are trees here. Yeah? And I click greedy. It will each time find the tree that is closest to the previous tree. So if I do it again, you will see that it starts here, finds the closest tree, and that's how you make your route. Pretty simple. You can code up pretty easily. This is sort of the greedy code. You have lists. You have visits are in the list, and you always search the closest. You add that to the list. You remove it from the visits that you still need to visit, and that's it. And you loop. Very simple algorithm that you can probably program in like 5 minutes, maybe less with like Claude or something. But it's Christmas. Greed isn't good. During Christmas, greed isn't good. And let me show you why. Imagine that instead of having this nice starting position, I have something like this. Now what will the route be? You see this? If you just look at this route that was greedily selected, this is not the best route. You have this very long line back from 13 to 2. Probably the best route was starting at 2, 1, 3, and so on. But with the greedy algorithm that we've written on the previous slide, it's possible that if you start at the incorrect location, you end up with something that's suboptimal. That's not such a good way to solve this. So if we compare these algorithms, and I'll compare them to a few other ones, the greedy one is fast. It is pretty fast. You just select the closest one, tuck, 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 tuck. It goes extremely fast. It's relatively scalable. Like even on big data sets, you just find the closest and you select that one. But it's not going to be the best possible route. It's going to be far from optimal because there are going to be decisions that just don't work that well in this structure. So let's look at something else. What would be an alternative to this greedy approach? You have a list, they go in a certain order. What could be a good alternative? Dijkstra, yeah. Much simpler. If you want to find the best solution that's possibly out there. Neural networks?
You try them all. You try them all.
Oh, we tried them all. It's very creepy because Henry's voice is right behind me in a big speaker. So when he speaks, it's like this creepy voice from behind me. Yeah, you try them all. You brute force it. You try all the possible combinations. And then you will always get the best solution. So let me add just a few of them. 10. Check, 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 check. There you go. Best possible solution. And it was finished pretty quickly. So that could work. There's only one problem. How big is our search space? Like, how many different combinations would we have to check? Does anyone know? Yeah, it's factorial. N factorial. So if you have n gifts, n factorial of options. Now, factorial you should always be a bit worried when someone is yelling something at you, and factorial by accident uses the exclamation symbol. So what if we have 5 gifts? 5 factorial is 120. Okay, 10. I don't expect you to know this by heart, but it is 3,600,000 and a bit for 10 visits. 10. That's the one I just did right before. 100 visits. 10 to the power 157. Now, our brains don't handle that number well because we don't see that number often enough. We can't really relate this number to something that's real and out there. I think I have a good analogy. The amount of observable atoms in the universe. Oh, there's whatever. The atoms in the universe. Everything that we have seen so far. The atoms. So the smallest little pieces. The search space for 1,000 gifts is like 10 to the power of 2,000. It's a ridiculous number. It goes crazy. Atoms in the observable universe. Anyone, any idea? 10 to the power of? All the atoms, like every little piece, a grain of salt. 10. That's not a lot. Atoms in the observable universe, 10 to the power of 80. So to give you an idea, it's 2,487 more zeros behind the amount of atoms in the universe. So that is a gigantic number. Now, these are still large numbers. And large numbers we don't deal with well. So I thought, if I make this demo, I can quickly show you just how long it would take to solve like 20 gifts, 20 steps. 20 doesn't sound like a lot, right? It doesn't sound like a lot. Okay, let me just add 20 quickly. Tick. 20. Oh yeah, it will take about 26,000 years. And you can see it's evaluating with like 1 million different options a second, so it's not going slow per se, but it will take a good 26,000 years. We have a bit of a problem. We have 331 days till Christmas. So, and those were just 20 locations, right? So we need something that's way more efficient than that. So brute force, ridiculously slow. So even for toy examples with 20 visits, it's already impossible. It doesn't scale at all, but it will if it finally finishes and the universe hasn't collapsed yet. It will find the best solution. But is that what we want? Good intermediate step. How good are humans then? Like if human planners need to do this, how good are they? Let's try. Oh, that's not fair. I put 5 and 6 on top of each other. Okay, anyone wants to guess what the best path is here? I hear 1, 3, 8, 2, 5, 4, 6, 7. Okay. Okay. Well, it's not that many, so I can just brute force this. 1, 3, 8, 2. So a different route anyway. So no harm done. It's normal. It was just to make sure that I can fill in this comparison fairly. Not to upset anyone, but humans are pretty slow in this. It took quite a bit to connect these dots. And this is a simple example with not too many other constraints. We're pretty slow at this. Can this be scaled? Nah. It depends. Maybe you can divide it a bit in sectors, and then you have different planners that can plan different sectors. That could work. And it's not going to be optimal, usually. It's just too much for humans to handle. Now, surprisingly, a lot of humans still have to do this, or they have a very simple algorithm that solves this. So there's a lot to be gained here. So we are going to use some Christmas magic to solve this. And when I say Christmas magic, it sounds better because what I mean is math. I mean probably math. Now, when I say math, I specifically mean mathematical optimization, which is just a group of techniques that allow you to solve these sort of issues. And I'm going to show you how to do that with Java. Because usually when I say math, I get this reaction, like, mathematical function. So we're going to do that slightly differently, and we're going to use the tools that you as Java developers already have. So I'm going to use a tool called Timefold, which is an open source tool that solves these planning problems. What we're going to do is we're going to model these problems as domain code, so just Java code, no calls out to C libraries, no neural networks, no LLMs yet. Relax. This is a non-LLM talk at the moment. It is open source, Apache license, so you can build with it whatever you want. And it is JVM based, so everything, the entire code base is also written in Java. So let me just show you what that will look like. Remember this? This was like our simple domain model that we were going to use. We have vehicles, we have visits. Now, what is the one thing that we want to change in this class diagram? What do we want an optimization tool to modify? The list of visits. So the list of visits, which visits are in the list and what order they are in the list. So with Timefold, you add a few annotations. It's very Java, right? Add some annotations and it magically works. So what this will do is it will, Timefold will see this domain model, and it will start reassigning and moving things around in that visit list, and it will solve the optimization problem for you. It will find the most optimal, or try to find the most optimal solution. We also need to give it an idea of what is a good score, because you can optimize, but we're going to minimize our travel distance. So it's pretty simple. All the vehicles that I have, just calculate the total driving time and then save that as a score. And this score will be used by Timefold to compare different solutions. Now, slides are cheap. Demo time. So since I'm live presenting in Ireland, I thought I would use Ireland as the chosen land for the receiving of gifts. And I have one Santa sleigh, and I have a bunch of different locations. And the green dot is where Santa will start. So that's his home base. Pretty close to Dublin, you're in luck. So how this eventually ends up is you can just press solve, and then Timefold will start moving the visits in that list around. And each time it finds a better solution, it will give you that solution. So the longer you let Timefold run, the more chances it has to move things around in the list. And whenever it finds a better solution, it will show you this. Now, you're seeing some lines appear. This is the path that the Santa will take. I thought, how can I make this slightly more interesting? Well, I have a Santa that I can trigger. So there he goes. You can see him deliver gifts. And that's the route he will take. And I can even move him back a bit. Okay, so that's how Timefold works. Now, I've shown you a demo. I've shown you some slides. Where does this fit in? So this is my visit class. Let me zoom in a bit. This is the visit class. Actually, nothing that special in there. The add planning annotation is add planning entity annotation on top. Are you familiar with GPA, Java Persistence API? You also need to add entity on top, because else JPA doesn't recognize the class. It's very similar to that. And other than that, a visit has an ID and a name of a child probably, location, how much gifts they're getting, the demand, and then some other things that I'll get into later. And then we, of course, have a vehicle. Oh, and this is where we find this, this piece of code. Also has planning entity, has a capacity. We'll get back to that one later. A home location and a departure time, just to make sure that it all works. Now, then we still need our lists of visits. Where are those coming from? You need to gather everything in what we call a planning solution. Basically, you create this class. Is it large enough for you to see? I can zoom in a bit more. Okay. So the planning solution contains everything that the Timefold will use to adjust things. So the planning entity collection, that's a list of vehicles. Can be one, can be multiple. And then we have a value range provider. That's basically the different values that it will try to put into that list. By gathering everything in this class and you pass this to Timefold, it will optimize it for you and it will start filling in that list. In the end of the optimization, you get this class back and you can just look on the vehicles what visits were assigned. That's basically the simple gist of it. Any questions so far? No?
Did it decided that it reached the most optimal point?
Okay. Okay, so I need to repeat the question for the online. So the question was, did Timefold decide that it was the most optimal solution, or did it just stop for a different reason? For the demo, I have it on 30 seconds. So the longer you give Timefold, the more time it has to explore this giant space of possibilities. And you can choose either to terminate after a set amount of time, or when a certain score is reached. That's configurable. But in general, the more time you give it, the better solution it is going to be able to find. Because of how Timefold works, and I'll get back to that later, it cannot guarantee that it's the most optimal solution, because the most optimal solution would require that you brute force it and that you check all the possible options, which it can't do. But it promises you to get the best solution in the time that you give it. So if you give it 30 seconds, it will give you the best solution it can find in 30 seconds. If you give it a day, it will give you the best solution it can give you in a day. Why is this important? Because businesses, like Santa, do have a certain day when that plan needs to be ready. The plan we would make for Santa would be useless one day after Christmas. So you could start solving now, and it will solve right before Christmas until it needs to leave. So it's really a business thing to check. Do I run it longer? Do I run it less long? And it's configurable. Okay? Okay, good. Of course, to dive a bit deeper into this, I heard Dijkstra's algorithm and so on. In the Java code, I showed you 0 algorithms. It's just domain classes with some annotations on it. Below Timefold, so what the solver does, the engine, is it uses meta-heuristics. And meta-heuristics is like a group of optimization algorithms. And we've selected the best default one for you, local search. But you can tune it if you want. The general idea of meta-heuristics is it makes a fast initial solution. So it creates a very drafty initial solution, and then it starts moving things around. And that's actually what you could see in the demo. It has a very quick first solution, and then you could see things moving about. That's how these things work. It explores by moving around. Now, how many moves a second does it do? Like, how many things is it moving per second? About 100,000, usually, in most cases. It depends a bit on how complex your system is, but it will move things around that way. And it's not just moving it randomly, it's moving it based on these algorithms. So it knows approximately what things it should change to improve the score. So these meta-heuristics are pretty fast. You get a fast solution. It's not the ultimate best solution, but you get a fast solution that works. It's scalable. You can scale this to 10,000 visits or more. And it is near optimal. And the near is very important because, as I said, we can't promise that it's the optimal solution because we don't do brute force, but we will get you pretty close to the optimal solution. So this has a lot of business value. So what we see often in these cases, not Santa, because Santa is magical, but in real business cases like post office delivery or garbage collection, it saves about 25% of travel time. 25% travel time means less fuel costs, happier employees, and just better for the environment, less CO2 emissions as well. But we still have a challenge. And to activate that challenge, I quickly need to change one thing in the code. Because we now have a simple scoring solution, but that won't scale. So we have actually a more complex, oh, go back for a second. Oh, no. I don't code standing up that much, so I can really feel my hands are like not in the right structure. We do have one more problem, namely if we make the problem a bit bigger. So I got Ireland small and Ireland, so the bigger one, that has 250 visits. If I solve this now, see, still pretty fast on a first initial solution and then improves it gradually. Okay, but now if I run this, Yes. Apparently did something wrong. Didn't I refresh the page decently? Okay. So normally, oh, it goes the other way around now. Okay, that's fine. There he goes. I know. Forgot one more thing. My apologies. Let me just get these in. Because Santa can't just arrive at any time. He needs to arrive when people are sleeping. You've never seen Santa, so he can only visit your house when you're actually asleep. So let me just show this again. Normally, I should have done it correctly this time. There he goes. There. You see it? Still have a problem. Instead of gifts, it's showing fire. Fire means the fireplace is still on. Santa tries to come down this chimney. Bad for Santa. The fire is on. And if I select it here, you can see that Ivy Smith is asleep from 9 to 5, and Santa arrives at 5:13. Problem, Santa cannot be seen. So there's something more that we need to take into account. So one thing that I changed earlier is we have regular variables that the solver will change, and then there's variables that depend on other variables. For example, the arrival time of Santa in a certain visit depends on the previous visit and where the vehicle started. So if Santa starts his travel at 9, then he will probably arrive somewhere 9:02 at the first visit. So to calculate that, we have something called shadow variables. And these shadow variables, arrival time supplier, are pretty simple methods where you state how to calculate that variable. So based on the sources, so based on the vehicle and the previous visit, the departure time, I'm going to calculate the arrival time. This is not something that Timefold moves around. This is something that Timefold will calculate based on the things that it has moved around. So if it changes a visit, it changes the previous visit, which means it will also calculate this. So now we have the arrival time and the departure time as well. So now we need to fix this problem, sort of. But we had this easy score calculation before, the simple one where we just...
Oops. You're muted again. You're muted again.
I get a small notification that this thing sometimes gets disconnected. I don't know why. Try one more time.
You're back. Then, you're back.
Okay, good. I'm going to try it one more time, and then I'll switch. So minimized travel time is a very simplistic view. Often that's not enough. There's other things that we need to take into account, and that doesn't work that well with that simple score calculation. In reality, we have things like drivers can only visit locations when they're open. Usually when you get your Wi-Fi, your internet installed, they give you like a time window between 8 and 12 in the morning. My technician should arrive. Don't always arrive that time, but that needs to be taken into account in the plan. Trucks have a very limited capacity. Like if you're doing garbage collection, once the truck is full, you can't get more trash. And multiple trucks can be scheduled at the same time. So these are all things that make planning even more difficult, especially if humans like manually try to do it. And I see some people like laugh a bit, like, why would humans ever do this? No kidding. I've been in places where they have basically said, Excel is our planning file. And they drag and drop Excel cells. And some companies still do this on Post-it notes on a wall. This is not Scrum planning boards, right? This is like actual operational planning. But that's what happens. So what we have been doing now, it's a pretty simple score calculation, won't work, but we have an alternative with Timefold, and that's called constraints. So typically, if you look at these sentences, you kind of want to translate them almost one-to-one to code, because that's the easiest way you can maintain code, that if it matches exactly what your business wants. So we have something called constraints. The syntax, I'm going to be honest, it's a bit scary the first time you see it, but once you get used to it, it's sort of normal. It's like reactive programming. If you see reactive programming for the first time, it's like, it's this. But once you understand it a bit better, it goes. So how do we define constraints? So for example, for travel, minimize travel time, I have it one by one. You select all the vehicles. So you get this factory thing in. You select all the vehicles. So for each vehicle, then you're going to penalize it. You're going to say this score is not good by the total driving time, which means that you are going to give it a worse score the more driving time your vehicles have. So that's how you minimize driving time. And you can also give that constraint a name, which is important because it will pop up in some of the UI components that I will show you later. So this is how you define minimized travel time, which is very readable as far as I'm concerned. Just the syntax is a bit weird because it's a mix between SQL and streaming, like the streaming API for lists and such. So a bit more complex one, vehicle capacity. So for each visit, check if the visit is assigned a vehicle, group it by the vehicle, and then sum the amount of gifts that you're going to give. So there's grouping and selecting. So if you know a bit of SQL, this should be fairly familiar. Filter where you don't have enough capacity, and then punish the solution for each increment that you're over the maximum capacity. So, I actually got this one by one. It's fine. Let me just show you what that looks like in our code here. So I have this vehicle routing constraint, and I have the minimized travel time. So that's basically what was already in the slides, right? So if I run this thing now, solve it again. There we go. You can see that the score up there, the soft score, is sort of getting better and better. It's getting higher because it's a negative number, so it's getting higher. That means that it's less travel time that has to happen to fix this route. Now, why did we have to give that constraint a name? Because Timefold doesn't just give you a solution, it also tells you why. Like, it gives detailed information on the constraints itself. This hasn't solved our fire hazard issue for Santa. So we're going to add another constraint that forces his visits to be within a certain time window. So not when the people are awake. He can only visit when the people are asleep. What does that constraint look like? I've already written it out here. That constraint looks like this. So for every visit, check if the finished time, which we know because we calculate the arrival and departure time with shadow variables, and then penalize it for each second it is outside that possible window where he can be visited. So these are all just Lambda calls, method references to Java code. So you're still just talking Java code here. Now that I've activated this constraint, I can actually run it again, and you will see that the lines are not as clean as before. Like before, if you just minimize travel time, it's a very clean, like, snake situation. But if you have to take into account when these people are awake, it's not a nice snake situation, because if you do the nice snake, then probably some of them are asleep when you arrive there. So it needs to take that into account. So that's what it's done now. I can even show you the score. So service finished after max end time. This basically says 0 matches means all our visits are within the time window now. Okay. Okay. I find it quite impressive, like how jumpy he gets when you try to do this. Jumps a bit all over the place, but this is just the best solution that Timefold was able to find while taking those constraints into account. So you can see it jump around, but it's all gifts. Santa doesn't get burned, and Santa is magical, so he can jump around this fast, probably. There's one other thing. I don't know if this is like a secret, but Santa sometimes has helpers. Like, he doesn't do everything alone. So here I have like 10-ish Santas. Let me just click the solve again. And then it will use these different vehicles, these different Santas to optimize these routes. So if you have 10 different vehicles and 100 visits, then you can optimize it like that. But there's a bit of a problem here. This is how these projects often work, by the way. You make a solution with 1 or 2 constraints, you show it to the business people, and they say, but this isn't possible, because Santa 1 only has a capacity of 12 gifts in his, he only has room for 12 gifts in his sled, but you're assigned him 40. Okay, what do we need? You can guess it. Another constraint. So let's add that constraint here. And that constraint is basically, let me just move this out of the way. The vehicle knows its total demand because it has the list of visits. So it knows for each visit assigned to it, it knows how many gifts it needs. It also has a capacity. So if the total demand is higher than the capacity, then you penalize it. You punish the solution. And you also give that a name. So now that I've activated that, you should see that when I roll this again, none of the vehicles now are going above their capacity. And I can even, oh, there we go. So you can even see that this is something you can show to your business. Like, you gave me these constraints, this is how the schedule is obeying them. Any questions so far? Nothing online, Henry?
Took me by surprise. No, they're chatting, but they're really calm on questions. All good.
Okay. If something drops in, just let me know. This was also just an informal mic check, I guess. Okay. So why would you use these constraints instead? Well, they read like business rules. And this is very important if you're talking to the business. Like, is there something wrong with the schedule at a constraint? Simple as that. It gives explainable score. So that's this little thing I showed you here. So it can explain why a solution is better or worse by comparing these scores and seeing at each constraint level why it's better or worse. And it's also incremental. That means that Timefold will not recalculate everything if you only change one visit. If you move one visit, it will only recalculate the constraints for those specific visits. Because what the alternative would be is you change one visit to a different vehicle, and you have to recalculate your entire score for your entire solution, but that would take too long. And because we use these constraints, basically, we can do this. If you add one package, if this is the before situation and you add one package, we will only really evaluate the last ones if you write your code correctly. Which means that you don't have to calculate the distance between the first 5 packages again, because you already know that distance and that travel time and so on. So that makes it quite a bit faster. So that was our focus for today, optimizing routes. I've shown you very simply with a few annotations how you can solve these sort of problems. We've minimized the travel time. That was the main goal. So that's done. We can have 1 or more Santas. I've showed you that in the demo as well. So you can have more Santas that will work together to solve this issue. And I added some constraints. I added capacity. So how much gifts can I actually give out? And time windows, that's to make sure that Santa only arrives when the people are asleep. And you can basically add constraints for whatever business constraint you have. Is that, oh, I need to drop off the packages in between. I need to make sure that 2 Santas are at the same location at the same time. You can model all those different problems as well. Now, what I want to show you is that this sort of...
There's one question.
Aha, go ahead, Henry.
It's more confirmation. So the constraints are always used as a penalty score. That's how it goes? Or
yes. So the way you write our constraints, you can either penalize, so give a penalty for things you don't like, but we also have the inverse, the rewards. So if there's things that are very positive for the schedule, you can also calculate that in as well. What would that be if there's visits that give like bonus score if you go there, like the very, very nice children? You might give a bonus if you meet more of those people. So it's more of a business thing if you use the reward function or the penalize function. I must say, usually it's penalize. You see a schedule, you see something you don't like, you add a constraint, and you penalize basically the thing that you're seeing and you no longer want to see. I think that that answers the question.
Yes, thank you.
Okay, good. So this sort of setup you can use for many different projects. The idea is basically model your domain, define some constraints, and then you just run it, and whatever time you give Timefold, it will find a good solution. Now, GenAI. How do you think GenAI works with these sort of planning problems? Because I had the idea when ChatGPT and such first came out. Interesting. This is the tool that's going to solve all our problems, according to the hype. What would happen if you give like your data, like your naughty list, your nice list, and your vehicles, if you give that to GenAI? So the answer in the room was it will tell you you're doing a brilliant job and will lie to you. Now, I was generally trying to use ChatGPT and such to solve these sort of planning problems, but it turns out it really can't. LLMs are mainly used to generate like the next most probable token, which is not with this search space, like these millions of different combinations. LLMs just can't really deal with that. But there's a big one. You can already sense it. What is Timefold? Code. What is LLM good in? Code. So these, I use Claude Code quite often to write constraints and such. It is actually pretty good at that as well. So there is this thing called Context 7. I don't know who of you has heard of Context 7. It's basically like a general purpose MCP server that you can connect to any MCP client. So that's usually like Claude Code or something. And they have actually indexed our full documentation. So if I look here for Timefold, it has indexed our Timefold solver documentation. So if you want to start coding with Timefold and you think, I'll just use an LLM like or Claude Code, you can hook it up with Context 7 and you will get more information. We also have added a custom GPT on ChatGPT. I've not made that public yet because I have a tendency to try to destroy that thing myself, and so far I've always succeeded. And it answers things that I don't want it to answer. That's why it's private and not public yet. So our documentation is actually pretty crazy. So our tool has existed for 18 years. It was called OptaPlanner before. We've rebranded it to Timefold. So we have about 500 pages of documentation if you roll it up to PDF. And that's explanation on how to use Timefold, but also the underlying optimization algorithms that you could choose. We have a default, so you technically don't even have to go look there. But if you want to change it, you can change it, and we have it written out how these algorithms work and so on. So that's why we get down to 500 pages documentation, which is even if you're just interested in the different algorithms we use, this is like a good resource to watch. So what you could do is you could start coding today. We have a quick start repository with a bunch of different quick starts. And actually the demo I gave was like a slightly modified version of one of the quick starts. So one of the quick starts we have, to get back to the beginning of the presentation, the toys need to be created. Well, we have a quick start called food packaging that will optimize how to package foods or create toys. We have shift scheduling quick start that allows you to schedule employees in a roster, also built with Timefold. And you know what? How much time do I have left? Well, I have a bit of time. So I'm going to quickly open the quick start for that one. Let me just stop this one and open the employee scheduling one. So the employee scheduling one has, as a domain model, an employee, as you can see. Pretty simple, right? An employee has some skills and name and when they're available or unavailable. And then each shift has a planning variable. So this is not a planning list variable, but a planning variable. And that's what Timefold will adjust. It will try to assign employees to these shifts. And it also comes with a bunch of constraints like, for this shift, you require a special skill. For this, you want no overlapping shifts because people can't typically do 2 shifts at the same time, 1 shift per day, and so on. And if you run this, there we go. Click solve, and it will actually optimize an employee schedule. So this is something that's in our quick start. I just cloned our quick start repository, and you can start exploring and using this today if you want to. So it solves these sort of problems. And Santa, this demo, is our vehicle routing quick start. So if you would clone the repository and you go to vehicle routing, it's basically what I've shown you today. So we have quite some time until Christmas. And there's so much problems in the world that we could solve with this. We even have school timetabling. Schools typically have like people full-time making the schedule of which class needs to happen in which room. We have a quick start for that. There's so much problems we can solve. And I think in conclusion, well, these sort of problems are very hard to solve if you don't use the right tool. And we can do so much good for a bunch of people if we get these things right. These employee schedules, if you can take into account more preferences, like I want to be off on Wednesday, even though I don't have days off. Minimize travel time just for the drivers themselves, can maybe go home faster to their family. There's so much good things that this technology can do, and I think it's not appreciated enough. And actually, I joined Timefold a year and a half ago because I believe that we can solve these problems across the world, and that's why we give this tool, Apache, open source licensed for everyone to use. And I think the biggest gift that you could give is take care of the people that you love. Use one of these optimization tools to solve one of their problems that they hate. And one of my neighbors is a nurse. She works in the nursing department. She became a nurse to help people. But unfortunately, she became the head nurse of her department, which means she has to make the schedule for the rest of the nurses. She did not become a nurse to make schedules. So she loves this sort of stuff. And I think there's many things in all our world that we could solve this way. So optimization helps you to take care of these problems. And I think the best gift you can give them is the best gift I can give you is to give a tool that helps you solve these sort of problems. All right, that was the end of the talk. I don't know if there are any questions. Yes, so there's one question here. Henry, go ahead.
Yeah. So Santa can travel as the crow flies, of course, radio flies. But how do you deal with roads?
Okay, so the question was, I'm going to be honest, I used Santa to sort of avoid this problem because getting the roads in there, the question was, how do you deal with roads? Because Santa can fly as the crow flies, which is our straight lines. What you typically do is you calculate the distance matrix up front, so the distance between 2 points. You use a map service for that, OSRM, Google Maps, whatever, and you feed that matrix to Timefold. So Timefold does not have the open source version does not have a mapping service included. We do have like a software as a service platform where we do have that mapping service done for our clients. But normally you calculate the distance matrix. So if you have 100 locations, you have a 100 by 100 matrix of the distance between each of those points, and that's what we optimize. Okay. Another question here in the back.
Yeah, really interesting. You mentioned that all the rules.
Yeah.
I'm just interested because I've got a very business-friendly syntax. I would recommend you use the Java syntax, or that's still an option.
Yeah. So So to reiterate the question, I mentioned that Timefold grew out of OptaPlanner, and that was very tied to the rules ecosystem. So that's like a business rule engine. We no longer support that because it's some performance constraints as well. So performance constraints is a bad name to now mention that you should use constraints. But we've created our own syntax that's way more performant and allows us to work incrementally. You change only one thing, you only recalculate that thing. And I'm not 100% sure, but I believe that the rules engine had some issues with that in the OptaPlanner version. So that's why we moved away. Henry, before I take any more questions here, are there any questions remotely?
No, I'm showing the comments of people happy with the talk. But
okay, good. That's good. That's good for my ego. Very good on my ego. Then I would say connect with me online if you want to ask more questions. Try out these quick starts that I showed you. There's so much good stuff in there for free. We have tournament scheduling. If you have a tennis tournament that you do for your sports club to schedule your tournament, school timetabling, bed allocation, we have a bunch of different ones. And I think this sort of technology now is a bit overshadowed by all the LLM and Gen AI hype, but this is technology that's existed for decades and still has a lot of applicability and business value to offer to a lot of companies. And I think that's why this is an important talk to give. If there's no more questions, I think we can just wrap it up.
There's one here.
Oh, good.
And I do agree with you, because people have a tendency to throw everything at Gen AI these days, and they do not solve all the problems, especially these kind of problems.
Mm-hmm.
So, indeed, the question is: do they use that at delivery companies? Do you know of any use?
That I can publicly state, I'm not sure. But I do know it's used, and if you go to timefold.ai, we have a nice banner with all the companies that are using us. I'm pretty sure I can just show that, right? If it's on our public website, I won't get into trouble. So
it's public.
Yeah. So IBM, Deutsche Bahn, ADP. So there's a bunch of companies that are using us right now. So if that's the right answer. And I think so some of these customers use our solver, our enterprise solver. We do have a platform where we have pre-built a full optimization solution like on-place shift scheduling or field service routing. And you don't even need to know Java for that. You just throw a JSON file at us, and we give you a JSON file with the assigned shifts back. That's it.
Yes. Someone is asking if Santa is using it.
Sorry, come again?
Someone is asking if Santa is actually using it.
I'm sorry, I signed an NDA. I can't. I can't go into details. Can't spoil that one.
Understood. Cool. No questions from the room anymore.
Okay, then I think we can round up. So one more question here.
Constraint factory and training variable, those contexts are provided with code engine, underlying engine you mentioned. Is it like it's like more declarative? We can solve any problem with the given.
You're on mute again.
This is incredible. We're at the end. So the final question, and then we're going to seriously round up. So the question was, what do these annotations, where do they come from, and how are they used? It's basically to give Timefold information on what it's allowed to change. So the add planning list variable was on the list that Timefold will modify. Basically to give hints. That's all it's for. So the framework knows what it's allowed to adjust and what it's not allowed to adjust. These are... Yeah. So these annotations serve the purpose that you can add as many fields as you want, and the solver will only change one or two fields. Everything is most of it is open source. We do have an enterprise version that has like for a few enterprise features. That's not open source, but the core and everything I showed you today is open, except for the platform I showed at the end. That's our SaaS offering. That's something different. Okay, and I think we can conclude. Henry, I would like to thank you for hosting me tonight.
It was my pleasure.
Thank you for dealing with all the mic disconnects for some reason. And I would like to thank the audience remotely. Thank you for joining all. And thank you here as well for Dublin Jug. The Dublin Jug gets a second talk. So
lucky you. Okay.
Yeah.
I'll end the stream and
yeah, thank you.
Enjoy your evening.
Yeah. See ya. Bye.